Hello everyone, I'm Ayush Srivastav. I'm a member of Group 17 for the video assignment. I am currently a fresher at IIT Guwahati.
Hello everyone, myself Manish Yadav and I am member of Group 17 for video project assignment of course Introduction to Computing Systems, and I will be explaining part A, B, C of question number 1.
Hello everyone, my name is Divyan. I'm member of Group 17 for the video assignment for the course Introduction to Computing System. I'm a fresher at CSC branch IIT Guwahati. I will be explaining question 2 for you later in this session.
Hello everyone. Today I'll be explaining the concepts related to question 1 of set 5 friends. Now starting with what is 2's complement. So 2's complement is a system of method for representing signed integers, both positive and negative in binary format. It is most widely used method for representing signed integers in a modern digital systems like computers and calculators because it simplifies arithmetic operations like addition and subtraction. Now we will see how 2's complement is different from other methods. So in other methods, first we will take sign magnitude. In sign magnitude, we usually use one bit for the sign and the rest for the magnitude. For example, if we take 4 bits, like 1010, in this, the first bit is reserved for sign. If it's 1, it means it's negative, and the rest bits are reserved for the magnitude. Similarly, if it's 0010, first bit is for sign, it means it's positive, and the rest are for the magnitude. Now, in one's complement, it is pretty much similar to the two's complement. Just the difference is that we add one bit in the two's complement. So now moving on to the next. So how to write a base number 10 in 8-bit two's complement format. So first we will be seeing for positive numbers. So here I've just given an example which I'll be explaining in a bit. And similarly for negative numbers, this is the example, and I'll be explaining this too in the next step. So just moving ahead. So this is the basic format. This is two's complement. So now I'll be giving an in-depth explanation for it. So suppose we take an example of plus 18. Now, if the number is positive, the representation method remains the same throughout. That is for sign's complement, one's complement, or two's complement. So suppose it is plus 18. Now we need to check the nearest power of 2, which is near to 18, but it is smaller than this. So it will be obviously 16. Now we will subtract 16 from 18. So 18 minus 16 gives us 2. Now this is a power of 2. So that's why we can simply represent 18 as 16 plus 2. Now this gives us the representation of 2 power 4 plus 2 power 0. Now we can, since we are doing it for 8 bits, we need to represent it in the format of 0 into 2 power 7 plus 0 into 2 power 6 going on, and then 1 into 2 power 4 plus 1 into 0 into 2 power 3 plus 0 into 2 power 2 plus 1 into 2 power 1 plus 0 into 2 power 0. This will be the entire formats. Now we just have to take the coefficients from each and our number will be formed, which will be 0, 0, 0, 1, 0, 0, 1, 0. Yeah. So that is our number. Now, suppose we are this will remain the same for everything. One's complement, sign, two's complement. The only difference is in negative numbers. Now, suppose we are representing negative 18. Now, what we need to do is we need to first take the magnitude of it, which will be 0, 0, 0, 1, 0, 0, 1, 0. We need to take this. Now, we need to invert all the bits in the first step. That is 1, 1, 1. We will invert each bit. That is 0 will get converted to 1 and 1 will get converted to 0. 0, 1, 1, 0, 1. So now we have inverted all the bits. Now to come, we need to add 1 so that we will get the 2's complement. This is actually the 1's complement. So adding 1, we will get to 0, 1, 1, 0, 0, 1. We will just do binary addition. So 1, 0, 1, 1, 0, triple 1. So the final result we get is triple 1, 0, 1, 1, triple 1, 0. That is the final result we get. So this is the 2's complement representation for minus 18. Now we'll move on to the previous slide and I'll just show these entire things. So yeah, this is exactly what I've written in the next slide. For plus 18, we can represent it as this, and this will be the 2's complement is the same. For minus 18 though, we will just invert the bits in the first step and then we will add 1. So we'll get this result. So now that we are done with it, we'll move on to the next slide. How to do binary addition? So for binary addition, we follow three basic rules. First one is 0 plus 0 gives 0. Second one is 0 plus 1 gives 1, or which is the same as 1 plus 0. Third is 1 plus 1 gives 1, 0, and it will be a carry of 1. Fourth one is strip 1 plus 1 gives 1, 1 with a carry of 1. If during sum of two n-bit binary numbers, summation has more than n bits, then the leftmost bit is ignored. This thing is special to 2's complement. Now we'll be taking an example to understand it better. So this is our example. In this, we will be doing binary addition. So let's look at the rightmost bits. So 0 plus 1 from the first rule gives us 1. Again, it will follow till here. All will give us 1. And then here we have 1 plus 1. So 1 plus 1 gives 1, 0, which is 0 with a carry of 1. And now again, we have 1 plus 1. So it will give 1, here 0 with a carry of 1. So it will be 1. So this is the result we get. That's how binary addition is done. Now moving on to the next topic, that is discussion on question 1. Now our main motive is to convert these sensor readings into 2's complement so that we can add them in binary. Now going ahead. Representing sensor reading in 2's complement binary format. So now moving on to method 1. Method 1 is nothing but based on the range of integers possible in 8-bit 2's complement format. To do it, in 2's complement format, we have 8 bits. We have a total of 2 power 8 possibilities, as each bit can take one value. So it will be, so since we have 8 bits, it will be 2 power 8. Now, the next thing is, by convention, we take the numbers to be minus 2 power n to 2 power n minus 1. In this range, we obviously have 2 power 8 numbers. Therefore, the range of numbers is from this. We calculated this to get this. Now, moving on. If any number that we get from the result of an arithmetic operation lies in this range, we say no overflow occurs. In the other case, we say overflow occurs. Now that we are done with the first method, we'll be moving on to the second method, how to check overflow. Now, with the second method, we will use the help of carry in and carry out on the MSB. While adding, we check the carry in and carry out on the MSB. If they both are equal, we say no overflow occurs. If they both are different, we say overflow occurs. Here I've taken three examples to explain it in detail. In the first example, we can clearly see that the carry in is 0, whereas the carry out is 1. So carry in is not equal to carry out, and hence the overflow occurs. In the second example, we can clearly see carry in is 1, whereas carry out is also 1. So since they both are equal, no overflow occurs. In the third example, we can also clearly see the same, and we can deduct it. For the second method, we're moving on to the third one. So how to check overflow? Method 3. In this method, we will be checking it with the help of whether the sum of two positive numbers is negative or vice versa. So when we add two positive numbers and the sum comes out to be negative, we say the overflow has occurred. Similarly, if we add two negative numbers and their sum comes out to be positive, we say overflow has occurred. So now here's the example for that. Here we add 5 and 3. So, but we get this, which represents minus 8. So we say overflow has occurred. Similarly for this, we add minus 7 and minus 2, but we get the answer to be 7, which is positive. So we say that overflow has occurred. So my part ends there. Hope you enjoyed it. I'll be passing on to solution of part A, B, and C for the first question to my friend Manish. Thank you.
Now, I will be discussing the solution part of discussion, starting off with part A. As we have previously discussed, the binary representation of x and y are as shown on the slides. For this part, we are going to discuss three methods. Method 1. In method 1, we are going to use concept of range, in which we are going to add x and y using binary representation, which results to minus 145. As we have discussed before, range of numbers possible are minus 128 to plus 127. Since minus 145 is out of this range, overflow occurs. Now, we will go to method 2. In method 2, we are going to use carry in and carry out concept, for which we have to add x and y using binary addition, as shown below. Here, carry in equals to 0, but carry out equals to 1. Since carry in not equals to carry out overflow occurs. Now we are going to method 3. In method 3, we are using the concept that if sum of two negative numbers results to positive number, then overflow occurs. Similarly, if sum of two positive numbers result in negative number, overflow occurs. So again, we are going to add x and y using binary addition. As shown, numbers added are negative, but summation is positive. Hence, overflow occurs. Now, we are going to discuss the solution of part B. As discussed previously, the binary representation of y and z are as shown on the slides. For this part, we are going to discuss three methods. Method 1. In method 1, we are going to use range concept in which we are adding y and z using binary representation which results to minus 160, and as we have discussed before, range of number is possible, range of numbers possible are minus 128 to plus 127. Since minus 160 is out of this range, overflow occurs. Now we will go to method 2. In method 2, we are using carry in and carry out concept, for which we are going to add y and z using binary addition as shown below. Here, C in equals to 0, but C out equals to 1. Since C in is not equal to C out, overflow occurs. Now we will go to method 3. In method 3, we are going to use the concept two negative numbers results positive, then overflow occurs, for which we are going to add y and z using binary addition as shown below. Here, the numbers added are negative, but the summation is positive. Hence, overflow occurs. Now, now we are going to discuss the solution of part C. As discussed previously, the binary representation of x and z are as shown on the slides. In this part, we are going to use three methods. In method 1, we are going to use the concept of range, in which we are going to add x and z using binary representation, which results to minus 85. As we have discussed before, range of numbers possible are minus 128 to plus 127. Since minus 85 is inside this range, no overflow occurs. Now we will go to method 2. In method 2, we are going to use carry in and carry out concept, for which we are going to add x and z using binary addition as shown below. Here, C in equals to 1 and C out also equals to 1. Since C in equals to C out, no overflow occurs. Now we are going to discuss method 3. The concept of method 3 is if sum of two negative numbers results in positive number, then it is overflow. For this method, we are again going to add x and z using binary addition as shown below. Here, numbers added are negative and the summation is also negative. Hence, no overflow. With this, I will now hand over the rest of the project to my friend Divyam.
Thank you, Manish, for explaining the previous topics. Now I will move on to the next question and explain the concept related to it. Now, what is left-hand and right-hand derivations and parsing, forestry? First of all, what is context-free grammar? Context-free grammar is a formal system used to define the syntactic structure of programming languages or any other format. It consists of production rules that describe how string in a language can be generated. It also defines how expressions are valid and also how can be created or structured. Let us see an example. This is a classic expression grammar. Here, code is converted into expression denoted by E. Then E gets converted into E plus T, which is term, or T minus T, or simply T. Then term gets converted into term into factor, which is denoted by T or T divided by F, or simply. Then factor can be converted into expression, which is written in brackets, or simply the constant or variable to which it can be converted. Parse tree we will see later in this session. Now, what are left-hand and right-hand derivations? In left-hand and right-hand derivations, these are two ways of applying a given grammar to generate expressions or string. Now, specifically seeing left-hand derivations. In left-hand derivations, at each step, we always expand the leftmost non-term. Let us see an example. For a is equals to b plus c. Here, goal gets converted into e, which is expression. Then e gets converted into e plus t. Then e gets replaced by t because it is the leftmost non-terminal. Then t gets converted into f. F gets converted into constant, which is represented as id. Now the leftmost non-terminal is t. T gets converted into f, and then finally f gets converted into constant, which is again written as f. Now let us see about right-hand derivation. In right-hand derivations, at each step, we always expand the rightmost non-terminal. Let us again see the same example. A is equals to b plus c. Here goals get converted into expression, which is denoted by e. E gets converted into e plus t. Here t is converted into f, since we are expanding the rightmost non-terminal. Then f gets converted into id. Now e is the rightmost non-terminal. Now e gets converted into t. E gets converted into f, and f then finally gets converted into constant, which is denoted by id. Now let us discuss the question 2. We are given the following context-free grammar. S can be converted into ASA or BSB, or S can be converted into A or B. Now the string which we have to generate using this context-free grammar is BB, AA, B, AA, BB. Now let us do the left-hand derivation. Here G is converted to S, then S is converted into BSB. We applied S converts to BSB. Then S is the leftmost non-terminal. Then it converts into BB, Then again we applied S converts to ASA. Then again we applied S converts to ASA. Then finally we applied S converts to B, and the resultant string is BB, Now similarly for right-hand derivation, here also G gets converted to S, then S gets converted into BSB. Now it is interesting to note that S is both leftmost non-terminal as well as the rightmost non-terminal. Now again we applied S converts to BSB, then again S converts to ASA, then S converts to ASA again, then finally S converts to B. So we finally get the string BB, AA, B, AA, BB as desired. This we have already discussed before, that the left-hand derivation and right-hand derivation are same because S at every step is both leftmost non-terminal as well as the rightmost non-terminal. Now what is a parse tree? A parse tree is a tree structure that represents the syntactic structure of string according to that formal grammar. The leaves of the tree are also called tokens. The internal nodes are the grammar rules or the operations that to be followed. Now let us take an example. Let us draw a parse tree for the expression x is equals to y plus z. Here we start with s, then it divides into three, x, the equal operator, then e. And e again gets divided into three, e, the plus operator, and t. Then e gets converted to t, t to f, and then y finally. On the right hand side, t gets converted to f and z. Now let us draw a parse tree based on the derivation we did before. Now we have shown the derivations again, and based on it, the parse tree can be drawn as starting from S. It is converted into BSB, then again S converts to BSB, then again S converts to ASA, then again S converts to ASA, and finally S converts to B. And hence we have generated our string B, B, A, B, AABB. For reading the string, you just read the terminals of each branch. And hence we have concluded our both questions. Now you can enjoy readings are behind the scenes.